Okay. Hello, I'm Viesula Sliupas. This is Mark Chalmers, and we are working on star spots on Pegasi. So stars are big balls of gas, or more accurately, miasmas of plasma. The star spots occur due to the magnetic fields of these stars. Because these stars are good conductors and due to their size, a phenomenon occurs called flux freezing, in which the magnetic field, the amount of magnetic field in any given area of plasma stays the same. So if you move it around, if you stretch it, compress it, the magnetic field lines come with it. In regions of plasma in which strong magnetic fields are embedded, the density of that plasma goes down in comparison to the surrounding regions with little magnetic field. What this turns into is the less dense regions of plasma rise up and burst through the surface of the star. At the foot points of these, dark regions occur on the star, and we call these sunspots, or star spots for any other body. These strong magnetic fields interrupt the convection that happens in the outer layers of the star, which leaves only diffusion for the star to emit heat, which is less effective, and therefore these regions are darker. So when these spots face us, the average brightness is lower than when they're not facing us. So we can use this to determine whether or not a star spot is facing us. In our experiment, we use a Meade LX600 camera with a CCD mounted on it. Once we get the pictures, we run them through programs to try to account for noise and any artifacts created by the camera, such as vignetting or just background noise.
So after we run our images through the programs to do image reduction, we make what are called light curves. Light curves are plots of brightness versus rotational phase, and shown here are light curves for every year that we have data from 2006 to 2014 through the V filter. And one cool thing to look at with the light curves is to note the change in amplitude and width of the peak from year to year, and how that varies, because that's associated with the shape and latitude of the star spots. So here, because Pegasi's average overall brightness changes from year to year, to demonstrate this, we have plots of all of the data from 2006 to 2014, so that it's easy to see what years are the brightest and what years aren't, and we can see how that varies. Now, in order to account for the overall brightness change from year to year, what we've done is varied the size of a polar spot on top of Pegasi on its visible pole. It's not unreasonable to assume that there is a large polar spot on Pegasi, because Doppler imaging in the past has shown there to be a polar spot. So in order to do this, what we've done is we've run inversions using light curve inversion of Pegasi. Light curve inversion was developed by Dr. Harmon, and what we've done is varied the size of the polar spot to account for the variation in average brightness from year to year. That keeps the average photospheric intensity the same, assuming that 2010, our brightest year, has no polar spot. It's not likely that this is the case, but what this does do is it shows us the minimum size of the polar spot from year to year, and also relative changes in size, if it is in fact the case that the change in size of the polar spot is the cause of its overall change in brightness from year to year. So here are our results. You can see 2006, 2007, 2008 through 14, with 2010 having no spot. And we would like to thank the National Science Foundation and Ohio Wesleyan University for funding us, and Dr. Harmon for his mentorship on this project. I don't know really what else.
Thank you.
Yeah, thanks.